Let's see. All right, it looks like we're live. All righty, hello everyone. Welcome back to another welcome back to another stream on my Magellan robot Kybernetes. So let's see. In the last stream, we implemented support for the INA21B current sensor that was in the logic power supply. For the most part, we just hacked in support here. There's not really well integrated. I mean, well, sorry, the support's there, but we didn't like put it in a driver module or anything like that. So today, what the plan is to I'm sorry. Okay. So today the plan is mostly to try to integrate support for the USFSMAX IMU, which is this Tindy device, or this device on Tindy that I found that claims essentially super high accuracy compass measurement, and as magnetometers are something I've always had a problem with, I'm willing to spend the money to get something that works, assuming it works. So kind of this whole effort has been to prep the motion controller code base to be good enough to handle the amount of data that comes out of this IMU. You know, this asynchronous I squared C, non-blocking access to I squared C, buffered operation, things like that. So today, so that is the goal for today, is to get some support for this IMU. However, there is one last thing that we need to take a look at before we implement support for this IMU. And that is just exactly how the Raspberry Pi and the Arduino communicate in my robot. And so, like pretty much every Arduino you've ever seen, I mean, I'm using an Arduino Uno in the in Kybernetes. So, like every pretty much computer and Arduino project, the Raspberry Pi talks over the USB to serial adapter that's integrated into the Arduino Uno. However, on one side it's USB, and on the other side it is a TTL serial UART, which is fine. It's just that interface is very timing dependent. It's not an extreme. It is a fairly reliable but not perfectly reliable interface. I mean, realistically, there is no such thing as a perfectly reliable hardware interface. There will always be some error that will crop up at the worst moment. So any good communication protocol will have some form of error recovery built into it. And so to take a look at and Kybernetes is no exception, and there have been many scenarios in which when I first started building it, I did notice that occasionally bytes will come across corrupted, occasionally bytes will get lost in that transmission. So I figure what we'll start with is we'll just do a really quick overview on how serial communication works on Kybernetes as it stands. And then we will improve the reliability, or we'll make it more robust so that we can deal with a higher data rate. And the reason I have been, I've been saying, oh, I don't know if it's good enough. Oh, I need all these other things. I did actually try to do support for this IMU about a year ago. I guess it was last September. But and it didn't work. But I had so many other things going on in my life at the time, I kind of just shelved working on the IMU for a while. So really a lot of this, the last couple of streams have just been, I knew these things were going to be a problem because I knew I had ran into them being a problem, and I knew I needed to change some things, and I just needed to find the motivation and also the time. So let's start with looking at how serial communication works in the current design. And so when we were the first video where we were setting up the packet handling. So we have this packet function where we looked at basically we see it starts the serial interface, and then it does this channel read on the serial device where it looks for a packet type structure or a packet type number, which in this case it's just a byte. It's an 8-bit, or I mean, it does say an enum class, but this is implemented as a a uint 8, and it's just a single 8-bit number. And what that'll do, so that tells that is the Raspberry Pi telling the Arduino, okay, what type of packet should I be receiving? And then what type of packet it should be receiving, and then it'll go into, based on what type of packet it should be receiving, it then handles that specific type of packet. So let's say a configuration set packet. We knew that the type was configuration packet, so then we have this type command packet, which is a configuration packet. And a configuration packet consists of, basically some configuration numbers and a couple of floats for configuration. But then there's a couple of helpers in here. Basically, the receive type command is configuration get. The send type is configuration set, and the transport size is defined as essentially how much data will be communicated. So that's 2, 4, 6, 8 bytes. 12 bytes, 16 bytes, 20 bytes. So yeah, so basically how large is the transport? What is the actual packet size? And so what this does here is it knows that it takes effectively the transport, it calls this receive packet function to get the contents of the packet. And what that'll do is basically just sits there and it knows what the type, based on the type, since this is a templated function, based on the type of packet that it's asking to receive, the send type, it has that number, and then it will read the channel for the number of bytes that is the size of this packet, and then it will then receive a checksum byte, which is a CRC8 CCITT. And so what it'll do is it'll read this data, it'll get the checksum byte, it then computes the checksum over all of the received data, which is the type value is the first byte in the packet, and then it will calculate for over all the bytes in the packet, and then return, verify whether the checksum is received. And so what this will do is it does ensure, it does ensure that the packet is received as we intended it to be transmitted. If they're, assuming that there's not a checksum collision, if the packet is received malformed, it should pick up on the fact that there was an error in transmission and drop the packet. But there's one major oversight in this system that I have here, and that is that while this readily handles data being corrupted in transit, it doesn't readily handle data being missing in transit. So if a byte has a bit flip, for instance, if any transmitted byte has a bit flip, this will pick up on it, because the checksum won't compute properly. But what will happen is, let's say that there's a packet missing or a byte missing in transit. But there's a buffer. The most likely scenario there's a buffer overrun on the Arduino. We transmitted too much data and we ran out of room on the receiving end. But let's, so this is a buffer over. We're actually missing, So the most likely scenario for a missing byte would be a buffer overrun where too much data is being transmitted and we overflow the receive buffer on the Arduino. The problem with the existing mechanism is that it's not nearly as tolerant of missing bytes. And the reason for that is that it is, there's no timeouts implemented on the Arduino side. So we don't know that a packet transmission started and then failed. So we should look at, in the future, implementing timeouts on the Arduino side, because they are implemented on the Raspberry Pi side. But the other big thing is that because we sit here and we forcibly receive, we wait until as many bytes as we're expecting to receive show up. If there's a missing one, we'll transmit a packet, and then let's say the next packet's coming in, or let's say there's not another packet for a while, and there's a gap. We'll just sit there waiting for this data that won't come. So one of the things that we would really like to have is a way to indicate that we are at the end of a frame. And so there are multiple, basically packing this into some kind of frame mechanism. And because we're using a byte stream, there's not, and this is a UART, this is an extremely low level interface. Just one quick second here. Sorry. All right. So because the UART is such a low level interface, it doesn't actually have a concept of like data frames. It just transmits a byte. Just a start bit happens, sends 8 bits, sends a stop bit. It doesn't handle. It's just this very simple interface. There's no framing. There's no packet delineation. That is entirely on the user of the device to implement. So we have to come up with some kind of protocol to indicate packets. And there have been multiple methods of doing this over the years. Probably one of the earliest is something called high-level data link control, or HDLC, which effectively what this does, the way that this works is rather than, the way that this essentially works is, assuming asynchronous framing, because that's what a UART is. Effectively, the way that this works is it reserves certain magic values to be sent that means something outside of the protocol. So in the case of HDLC, if the receiver ever sees a byte that is equal to 7E, it means it's the end of a packet. Like, it's just this one random reserved value that means that this is a packet boundary. But what if there is this value 7E in your data that you're transmitting? Like, you can't, obviously, if the 7E byte occurs in your stream, you're going to trigger the end of a frame, and then all hell, your packet won't be sent correctly. So it also adds a magic value called 7D, the value of 7D hex. And what this means is it's an escape value. Any byte transmitted after this is assumed to be a non-control character. And so the other thing that this does is, in order to try to prevent 7E from showing up the line, it flips one of the bits. And the reason that it does this is that, let's say you did want to transmit 7E in your data to indicate that there's just a byte 7E in your data that you're transmitting. If you were to send 7D and then 7E, well, there's 7E, the packet boundary happens. So what you do is you actually flip a bit, canonically bit 5. And so a value of 7E being transmitted will not actually be 7E after that control escape. So this is one method of transmitting, of building a framing protocol on top of a UART. And it functions on reserved values. So this works pretty well. There is also, again, one major downside of this, and that is, let's say the value 7E shows up a lot in your data. It is admittedly only one of 256 possible values, but let's say it shows up a lot. Let's say you have a data stream and 7E might show up enough. You end up with one of these control characters for every instance of this value 7E in your data. So you don't know when you're transmitting just how large the transmitted data might end up being. If you were sending a string of 7E, worst case scenario, you will double the size of the data being transmitted. And if you transmit a packet that has no hex 7E in it, it will have no additional size. Or it'll only have one byte of additional size. So this might be fine. It might not be fine. So there was another protocol, or there's another. This was a bit later. There was another protocol that was invented to try to solve this, and this is called consistent overhead byte stuffing, and it's a bit more complicated to understand, but not that much more. And so the way that this works is it reserves a special value 00, or just 0, that indicates a packet boundary rather than HDLC's control value of 7E. And so if the value 0 occurs in your data, that would be end of packet and cause problems. So how does essentially the escaping mechanism in COBS, or consistent overhead byte stuffing, COBS, COBS. I'm going to be using COBS probably from here on out. The way that this works is rather than defining a specific escape character that you would transmit to then indicate the next byte is something that or to indicate the next byte is one of these pre-reserved values. Rather than doing that, it actually sends a pointer, or the first what is called the overhead byte is effectively a pointer to the next 0 that would occur in the stream. The next reserved value that would occur in the stream, which in the case of COBS is just 0. That's the only one. So if we were there's some examples. The Wikipedia page on this is actually really good. So the way that this would work. So let's say we have 11, hex 11, or 11 hex, 22 hex, 0 hex, and 33 hex. We'd effectively say that the first byte we transmit is 3 bytes into this data stream. You will find the 0. So you send the 3, and then the first byte comes through hex 11 hex unmodified because it's not a reserved character, and then the second byte 22 hex comes through unmodified because it's not a reserved character. But then the third character comes through, and we know because this overhead byte said that the third byte will be a reserved value. We know that this is actually supposed to indicate a 0. And in order to make this overhead consistent, what we do is we then send the next pointer we use this byte to indicate the next pointer to 0. So in this case, it's sending essentially 2, because this packet is only 4 bytes long. So 2 points to the end of the stream. Or points to the end of the stream. So realistically, it's okay for any value to be populated here, because it's going to point beyond the end of points either to this last byte, the byte beyond the end of the packet, and or just something into the future. Essentially, this if you had a much longer packet, this would just then point to the next 0, and then that would point to the next 0. And then at the very end of your packet, you then transmit 00 to indicate the end of a packet. And so with this, yes, Danish, correct. Reliable transport over unreliable I would say reliable connections over unreliable transports. You can't depend on the underlying hardware to transmit the packet correctly. It will usually transmit correctly, but not always. And we're trying to figure out a way of detecting to build a reliable communication mechanism over that. And essentially, the way that you achieve that is by implementing some error detection and then error recovery. And this, at the very lowest level, this part itself is not the reliable part. We're just establishing the lowest level of the reliable component, which at the very base is just to know what are the packet boundaries. And so we will then continue to build on top of this to implement to achieve reliability. So at this level, we're just trying to figure out what are the packet boundaries in the stream. And the next step on top of this will be essentially using some kind of checksum or to detect whether the contents of the data were received, or the contents of the packet were received correctly, because this will start to solve our did we receive a whole packet, or did we receive a packet at all, and then above this we then need to know if the data was then mangled in transmit, and then above that you need to know whether the packets were received in order, or a particular packet did not come through, or something. So at the very lowest level, this is just what's called a packet framing system. So we're going to end up having to do a whole lot of work here in order to convert my robot over to using this COBS mechanism. Here's also further down. Here's a bit more of a good explanation of what's going on. I believe there was also a Python library called COBS that helps you do these conversions. But I see that the Python host it doesn't seem to have ever gone beyond 1.0. So I don't know if this is maintained anymore. So 2010 was version 1, and it's now 2025 as of recording. And who knows if this has been updated. So we might just go ahead and make our own here. And obviously the Wikipedia article comes with some C implementations of this protocol, which we may or may not steal. Borrow. So is there an expected latency threshold? So for a UART, which is typically a point-to-point connection, and because we're inside the robot, the expected latency would be very low. It'd just basically be some small multiple, some small fractional multiple of however much data was being transmitted. So let's say we're transmitting a packet of 25. I believe I'm running the interface in here at what am I running it at? I think there's configuration actually. MCU config. I think I'm running it at 250 kilobaud, or 250 kilobit. Yeah, so 250,000 bits per second, 250 kilobits per second, and because the UART has is a 10-bit, 8 bits per 10-bit frame, basically pretty much any UART you encounter on a microcontroller is going to be a 10-bit frame, or 8 bits, 10 bits transmitted for every 8 bits of data moved, because there's 1 bit to indicate that a transmission is starting, 8 bits of data. Like a different means for slower connections. Not entirely certain I understand the question. Different means for, is there an expected latency threshold? A different mean. So at this level, we're not worried about latency. But above this, usually you would define latency targets based on the expected throughput of a connection, and which, in the case of something like, it's basically going to be a function of the expected throughput and the expected distance of transmission. In this case, we're not expecting much more latency than just the underlying transport has. But I'm not entirely certain. I'm not entirely certain I've answered your question. But let's see. All right. So, oh boy, where to even begin on this? Again, I don't pre-plan my plan of action much for these streams. So, if we're looking at the motion controller logic, so we are basically going to start by, okay, so probably the best place to start attacking this is going to be the send packet and receive packet functions on the motion controller, and also the corresponding send and receive packet in the Python code for the logic in the robot. All right, so if we look at this transmission function, we have, so basically I think the way I need to go about this is we'll take the receive packet function, and the transmit receive, and rather than trying to potentially improving the protocol at this point, we'll we'll just do a direct swap of the communication mechanism, and then we'll start to take advantage of any improvements that it gives us. So, as we said earlier, the send packet and receive packet, the current protocol as it stands, is we'll send the byte, we'll send a byte for the type, we'll then send the data, we'll then send a CRC8 checksum, and that indicates a packet. And then in order to have sync, in order to synchronize the connection, the way that had worked, because I'd said that this isn't very tolerant of missing bytes. The way that I currently get around that fear is if I do detect a desync or an error in transmission, the way that I handle that is I send my synchronization packet is just a packet. I reserved a command byte for synchronization, which is just sending all ones. And the way that this works is I figured out the largest packet that could be transmitted, or the largest packet that I would sit around waiting for, and I send at least that many sync bytes, or sync commands. So hopefully I will free up waiting on the previous packet, and then I will just send basically a byte that expects to no response, or it won't generate a response. And so if I ever detect in an error scenario, I just start flooding the bus with a byte that essentially is like a no-op command. But that's not particularly efficient. So what we shall do? All right, so let's just send it. Okay, so we will start with here, which we have well, actually we send packet. We do have to send the type. So yeah, we'll start with we'll do one direction. We'll do one direction in COBS first, and then one direction in old format. So or just to start with. So let's start with this COBS encode function, which the way that this works is you give it a data packet. It then iterates through this and then figures out where all this data should be. But what we'll do is I just want this COBS encode function. Essentially, rather than buffering the data that we're transmitting, I'd just rather emit it straight to console here. So what we'll do is, so send packet, we're going to just comment out the old one. Template. Type name channel, type name T, bool send packet, channel T packet. All right. So we're gonna have our type, which is const. We're really only using an indent of 2 here. What the heck? What happened here? Really? All right, because this started off as a Arduino sketch, and that only uses an indent of 2. Sorry, just little lucky type equals. Let's do int 8. Receive type. All right, so what we'll do is. Code page is buffer, or encode is buffer, encoded byte pointer. Encode plus encode. Okay, rather than doing this plus encode thing, this is just going to be our transmit function. So we're going to start with, we know that our command cannot be a 0. We'll just take advantage of that fact. So you see packet type, well, I mean, none is a 0, but so what we'll do, so actually, all right, fine. We shall COBS encode. Fuck. All right, so we're going to just immediately transmit the output code pointer. Code pointer 1. Buffer. Code plus plus. Is there any reference to encode? Code value. Code byte pointer. Code 1. I hate when people do that. Basically, so basically what we're trying to do is we know essentially the buffer that we received here is not fully, because this just takes, if you have a buffer you're trying to encode in COBS format, you'll just take the input buffer and how long it is, and then it will output a buffer. Just the thing is that with this, the way that I have this send packet function is that there's an array, there's a byte array of data that we know to transmit, but that the actual type byte is not part of that array. So all we have to do here is byte not 0, write it. We just have to basically well, okay, we're just going to, for the sake of simplicity, we're going to assume that the type cannot be a 0 byte, which for the most part is true, but I guess if there's a failure there's a none type. But so yeah, so we'll just assume that the first byte transmitted is non-zero. So the first thing we'll do is just encode. We do need to transmit the overhead byte first. So well, fine. Might not 0, write it. Encode plus plus. Because basically what we have to do, because we have to scan the byte stream for essentially 0 values, we do need to know where, with the first byte we need to transmit onto the wire is actually the is that overhead byte. So we can't actually just immediately place the packet type on the wire. So what we'll actually, so you know what, we can just assemble. We should just assemble the packet here. I think the longest, how much stack space did I allocate? I only gave it 128 bytes. I don't want to do a dynamic allocation. So what we'll do is code pointer. Yeah, so that is one of the trade-offs for COPS here is you do need a transmission buffer. So I guess I ought to do that. So what we'll actually do is who calls send? What can call send packet? Can I end up calling send packet from both main threads? I think I can, which is unfortunate. Yeah, I can send packet from the main thread, because I think controller update can call send packet. I'm pretty sure call send packet. Yeah, okay, both threads call send packet. So sorry, the fear here is that it was like if I do a stack allocated buffer for my transmission buffer, a packet assembly buffer essentially, we'll end up with a problem. Or I don't want to blow out the stack. So we'll just we'll bump this up to 192 on both of our threads, just to give us some breathing room on using a inline transmission buffer effectively. So what we'll do here, we shall say uint 8 transmit buffer. We'll just say 64. There's our transmission size, and then if we ever exceed the size, we'll assert. So we shall do. We've got our encode buffer. Our encode is our buffer. We'll then do. We'll just copy this out. Yeah, we're just going to copy it out of Wikipedia. I know this works. Encoder. That's not what. Wow. Encode buffer. Code pages encode plus this encode plus plus. Output code pointer, and we'll do code equals 1. And then we have to do our basically our magical override here, where we know we're not putting a 0 in here. So we'll do pointer to encode plus plus equals const uint 8 receive type. Actually, we don't even need the that part. Right. And we'll then do if byte, then we do that. Otherwise, we have to do a code thing. And what we'll do is for const uint 8 underscore t. Wow. Underscore t byte equals const uint 8 underscore t. Well, you know, range overcast. Packet. Oh, geez. Length minus plus plus byte. All right, cool. I think I got that right. Yeah, so byte starts as a pointer to the packet data. We're going to transmit as much as there is length, and then minus byte. All right. So and and encode not equal buffer plus 64. Basically, we have to basically put an end case that we don't exceed the size of the transmit buffer. Otherwise, we're screwed. So actually, what we need to do here is before we do any of this, we also need to calculate the CRC of the data while we're encoding it. So say CRC 8 equals 0. And then say, actually, CRC 8 equals, calculate CRC 8. It always starts at 0. Oh, Jesus. Encode 0. And no, encode 1. Sorry. Why did I make it give me a pointer? I'm sorry. As we're doing this thing again like we had before. Type is receive type. Type size of 1. Size of type. Why not? Okay. Cool. And then what we're going to do is so we have our first CRC8 calculation. We're then going to say CRC8 equals CRC8. Let's calculate CRC8. CRC8. Pointer to, or actually, we can just say byte and size of 1. That's not the most efficient way of calling this CRC function that I built, but whatever. we'll make this more efficient later, you know. This is lookup table, program read byte. Okay. Oh well, we'll make this more efficient in the future. No worries for now. Yeah, CRC8 will transmit that, and then we'll say if byte and pointer to encode plus plus equals byte and code plus plus. Basically, code here is the overhead byte. We're effectively calculating the offset to the next 0. And then otherwise, if not byte, or we've hit essentially the maximum encodable value. So that was the other thing about COBS that I didn't mention before. So that overhead byte, being a pointer to the next 0. What if we exceed the amount of data that we can, 250, 255, 250, let's say the 0 is more than the number we can actually say. We have to if no zeros ever show up and we have a long packet, we actually have to cap out our code value at FF. Every 255 bytes, we must retransmit an overhead byte because we're just run out of essentially pointer value. And there's a reserved value FF, or 255, that indicates that there actually is no 0 byte. So that's what this condition does. And so the code page, or the code byte pointer is just code. We reset code to 1, and then we say the code pointer is now the current value of the encode block. And then if the byte was in fact 0, or we've run out of or length, or so if the byte is not 0 and or we have enough length to end. Actually, what is the check? Yeah. So if not, but or like plus plus encode. All right. Whatever. Plus encode. Okay. At the very tail end here, we then code pointer is code. All right, and so encode our data to be transmitted. COBS encode our data. But then we also have to encode the CRC byte at the very end of things. Yeah, no, maybe. There's a better way of doing this. Hold on. You know, this is C++. We could potentially use... I wonder if it actually let me use a lambda function for this, because we could basically write a function of this is what it takes to encode any given byte. You know, let's see what happens. I think this will actually, if we say return 0 right here, it'll probably compile. Or not. Oh, that's what I did. Yeah, okay. So we know that we haven't broken the compilation. So, all right. So let's do this slightly differently. Let's define... what it means to encode a byte into this. So, hold on before I undo that. All right, so auto encode byte equals, I'm just going to reference capture everything, and then we're going to say uint 8, see, byte. Can I actually do that? Well, hey, yeah, look at that. Maybe. So sorry. So what we'll now do, we'll recapture the crux of this inner loop. So let's say crc8 equals calculate crc8 the byte, and then size of 1. And then we'll do all of this inside stuff. So if byte, you know, we'll just call this b. B, if b, then encode plus plus equals b plus plus. If not b or code equals ff, then let me just copy all this stuff we already did. Not b length and code. All right. And then what we'll do is okay, so now that we have our transmission function, we calculate a CRC of the byte that we're submitting. We then do our encode function. Okay, so we then honestly, I mean, that should be pretty explanatory. Right, our final code value. Ah, right, the final code value. So what we'll do is, so now we encode our type byte. Say encode byte. This is going to be where we use the type. So, we actually don't need this const type thing up here. Byte receive type, we don't need that. We'll do our receive type, and then we'll do our big loop. Our packet data. And then we'll add our CRC byte. Actually, yeah. So plus 64 would be, yeah, we've reserved 64 bytes of data. So we need, we are always going to need, actually, yeah, it's 61. Ugh. I'm trying to think of how much data we would need at the very end. So if we did buffer plus 64, that would essentially be there's no data left in our transmit buffer. If there is... Yeah, there'd be no data left in the transmit buffer. So we do need to reserve 1 byte for the final 0 that we'll add. We then need to reserve a byte for the CRC. So that would be 64 minus 1, so 63 minus another 1, 62. But we might need to put in an overhead byte in case our CRC is 0. So we'll say 61. Actually, just to make sure I'm in the clear, I'll do 60. So we've got we calculate our CRC. Actually, we don't. Sorry, right? We don't need to do any of that anymore. We then just call encode byte on each byte of data. So pointer to byte. Is there a better way of doing that? For increase while we still have length. Yeah, I don't even know what's more efficient. Sorry. Yeah. So byte length. Yeah. Whatever. And for packet, so we'll say byte plus plus, and we don't need to do this backwards length thing. I mean, we could. I mean, that's fine. Whatever. We'll leave it. And we do encode checksum. And we do our okay, yeah. And then we do our final overhead byte update. Then we'll write the last byte available to a 0 to indicate end of packet. Actually, we don't even know how many bytes are in our encode buffer now. We could say square t. Length. So actually, we'll just do encode pointer minus the buffer pointer. That'll give us the length. So we can now do return chanwrite equals 1. Oh, that'll say the number of bytes actually transmitted. Okay, so we're going to say auto ret equals channel write the channel, the data, and then encode minus buffer. I'm going to say return ret equals encode minus buffer. Oh. Length not declared in this scope. Oh. honestly, our length is going to be a transport size plus 2. That's a. I think that got reflected in the Python code base. Or not. Maybe. One of these. Oh, I see. Transport size plus size of pit frame. That's right. Okay. So, because 19 would be 1, 2, 3, 4, 8, 10, 12, 14, 15. Oh, it's 19. Why is it 19? Oh. How big is the status pack? Oh. It's because 4 byte, 4, 5. It's 5 bytes. Okay, so I need 5 motion controller state. Was that the 5 bytes? Oh, that's 1 byte. 1 byte. So 5, 6, 7, 8, 12, 14, 16, 18, 19, plus the size of this bit frame. Okay, yeah, so the transport size, that's all fine. Okay, so we need our length to be transmit size plus 2 in order to encode, in order to have space for our... Actually, nope, that's wrong, because this length needs to get subtracted. Oh, dear. Because we need to... okay. Rethink this a little bit. Actually, yeah, we'll just do that. Like minus code byte. Or length. But we want length to be true because... we want length to be true here because at the very end of transmitting this packet, because we do need to encode one more byte. Okay. Sorry, because we're encoding this internally, we don't need to worry about it anymore. So... crud. Yeah, actually, I love C++. So here's what we're gonna do. This is I'll be honest, a little. No, can't do that. Sorry. I was gonna say we could declare a struct on the fly to contain our transmission packet, but no, that'd be horrid. So we do this encode byte. We need an external length calculation. Length. If it was 0. Okay, yeah, so if the byte is still 0 or okay. Yeah. You know how we're gonna do that? We're gonna define a Boolean for end. If not, by and not finish. There we go. We'll move the length back down to here. Finish is false. We'll do encode byte. Finish. There we go. That'll do it. It's basically what we're trying to do is I'm sorry. So essentially what I just did here was if the byte that was asked to be encoded was a 0, the idea was it would then if the byte that was asked to encode was a 0, the first, or it ran out of space, because this is, if it was a 0 or it ran out of space, what it would do is it would store the last code pointer, but then, or it'd update the last code byte, and then it would reset the code counter, and then update where the next code byte will go. But the problem is that if we ran out of space, or if we had hit the end of the packet, there really wasn't any point in sending a new byte. So what we would, or if this will run whether we ran out of space or it was a 0 to encode. But if we actually did need to encode a 0, we then need to, was that an or? Yeah, so if the current byte is a 0 and or there's still data to transmit. So we could say in this case, if it was a 0, there's more data to push. We have to write that 0 into here. So we have to populate some bit of data there. Or also would bail out if there's no, if we hit the end of the packet. So yeah, so we encode, so length would be true if there's any data left, if it's not the last byte. So what we'll do, what we added was a Boolean to indicate whether it's the last byte. And so we replaced checking if there's length with it not being finished. And so by default, we don't want it to finish, so it's false. So we'll encode a byte, it's not finished. We'll encode all of this packet data, it's not finished. And then we do want to encode our checksum, and then we have to do our finalization. And then set the last thing to be code page. Okay, so code page could be, so the worst case scenario is the new code page could be this, but we don't necessarily, but we will end up populating that code page. Plus encode. Show return size encode minus buffer. Code. Pointer encode plus encode minus buffer. Okay, I think that'll work. That'll work, right? Maybe, hopefully. That's supposed to be channel. All right, make perfect. It built. Hopefully that does what we. Hopefully this does what we expect it to do. Also cool that we can use lambda functions in C++ on Arduino, assuming we're not trying to use a standard function. So. Anywho, all right. So we have modified our transmission function to use COBS. We then need to modify the receiving side on the Python logic. So our receive packet. All right, so let's see. Python COBS library. PyPy COBS pip install COBS. Oh, so there is a COBS library. I'll just provided. All right. Well, let's see if we can use this Python COBS library. So obviously, I don't think it'll be installed. So from COBS import COBS. Obviously, no COBS. So what we'll do is we'll pip install COBS. Maybe that'll work. Indices. Hey, look at that. We'll add that to a requirements file here. COBS equals 1.2. Cool. All right. So in here, we'll do a all right. And do any sort of adds to that, right? Now, length, transport size, encode byte. Perfect. Aye. The send sync packet's going to be somewhat of a problem. Bytes should be a 15-byte receive. Okay, well, you know, it's fine. Probably. Yeah, whatever. All right. So we'll do our receive packet. So the way that this works is we wait for the way that this has worked in the past was the first byte it receives is exactly 1 byte, which is then our type ID. We then look up in this Python dictionary or type int to a Python type. Because using Python's dynamic typing here, or the fact that types are also objects, right? And then and where's the receive function? Sorry, receive, and then we wait for the data of exactly how much that's supposed to be. We get the remote checksum, we compute a local checksum, make sure that everything's valid. And then if we have an invalid checksum error, receive packet, async loop, we receive Oh yeah, and I think if the calling function invalid checksum error. Yeah. Well, I'd completely die if I have an invalid checksum. Oh, that's interesting. I guess I never actually implemented retry on the receive side. Oh dear. I'm surprised I haven't. Well, I wonder if any of those failures I have had are due to that. Huh. Huh. Alright, well. Interesting. What we're gonna do, so we'll have to redo this. Oh, not redo this. We'll change the way that this works. We will read self.reader.read until separator is found, which is going to be 0 byte. The coroutine type any. All right, yeah. So basically, we're waiting on a basically just a hex 0. So yeah, we'll say packet is well, not packet. Cobb's packet equals read until 0, and then we will do. We then need to decode that. Cobb's, I believe it's just Cobb's.decode, right? Yeah. It starts off with a hex 0c. Okay, actually, you know what? We're just gonna experiment a little bit. So yeah, so if we've got from Cobb's import Cobb's, and then we're gonna say we're gonna have a byte array, so data equals binary hello world. I'll put a random null character in the middle of it like it was demoing hello world. Data dot len length, or is it len data? Yeah, that one. All right, so we got 5, 6, 7, 8. Whoa, hold on. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Cool. Let me just make this not so ridiculous. There we go. Should be 13. Yeah, and then we say packet is Cobb's encode data len data len packet, and then packet. It'll show us that there's a the overhead byte is there's going to be a 0 by 8 in, so that's 1 2 3 4 5 6 7 8. The 8th byte was a 0. And so 1, 2, 3, 4, 5, 6, 7, 8. And then the next pointer is a 6, but that's off the end of the string. So 1, 2, 3, 4, 5, and then end. All right. So then if we were to say packet.extend with 0. Oh, wait, it's not a byte array, it's just bytes. So equals byte array. Foo, or one foo, and then foo.extend with packet foo.extend 0. Really? I don't remember how this works. Fine. Alright, foo. Yeah. So then if we did Cobb's decode foo. Oh, 0 byte found in input. It doesn't like that. I guess we have to trim off the... Alright, so if we have a Pi serial, which I think I'm using async serial. Yeah, Pi serial async IO. API. I just want to know if the read, because it has a reader, like the read until. Great. Maybe it's just the Python serial API. You know what? Let's see. There's gonna be a read until. Oh, read until none. Byte string to search for, read until sequence is found, size exceeded, bytes unavailable, string otherwise. The question is whether read until will. The question is whether read until will include the byte that we're scanning for. Oh, come on. No, fine. Oh, that's async IO streams. Okay. On success, the data and separator will move from the internal buffer. Return data will include the separator at the very end. Okay, cool. That was a lot easier than trying to look this up on the internet. Okay, that's funny. All right, so say Cobb's packet dot trim. No. That's gonna be a bytes. Cobb's packet. I'm trying to remember the Python notation for this. How do I remove the last a Python object with a Python array without the last byte? So if I were to say r equals 1, 2, 3, I think it's like -1. Yeah, that's what it is. 4, 5. Yeah, there we go. Okay, cool. Receive the Cobb's encoded packet without, but drop the trailing 0 byte. Okay, cool. Cobb's packet. There we go. Awesome. And we'll do await. We have to do await. There we go. Perfect. Will be a byte. Perfect. We'll say packet. Actually, we'll just say packet Cobb's packet contents equals Cobb's dot decode packet Cobb's, and then this will be. And continuing R, if we do 1, yeah, that also is basically everything with awesome. Okay, that'd be minus the first, without the first and last elements. Perfect. So do packet type ID is, just call this contents. Contents 0. And then data is contents 1, -1. And then checksum remote is contents. I think our that was without the last. I want the last though. I was trying to remember. It was -1? Yeah, that's what it was. Okay. Contents -1. Python indexing is kind of funny sometimes, let's be honest. Yeah. -1. And then hash bytes plus data. So that's going to be contents -1. We're going to use every possible indexing thingy right here, of course, you know. Cool. Digest, checksum error. All right, let's try this. I think we've actually built up enough. Yeah. Okay. Packet cobs is this. Wait until 0 byte decode. First byte. Do the type ID. Contents is the middle block. Remote checksum is the last. We're going to do a hash of everything up to the last byte. And then p-type and move. Okay, let's try this. So we're going to, on this side, we're going to make clean, make. We're going to SCP build motion controller over to the robot. We're then going to do AVR dude. I'm going to flash this to the onboard microcontroller. Turn on our thing. Then we're going to do our good old remote control program. Well, that did something. Maybe. Well, let's see. Oh, it's regulated on going backwards. Okay. You know what? It's actually working. I can't believe this. You know what? It actually is. It's actually running. We are getting reliable data transmission somehow. Let's set up the camera just so we can see. I should say reliable data transmission. I didn't break it. We are receiving this COPS formatted data successfully. So let's go to the phone cam, and as we can see, we'll do the find. I'll run the find cone program here because it's a little more regulated. Loading. Perfect. It's slowly running. Yep. The fact that it's actually running around means that we didn't blow up the protocol. And the data's coming in from the robot, desktop. Still see that the data is in fact coming in from the robot, which means we are transmitting from the microcontroller back to the computer, which is good. Now we need to do the other side. Wow, I hate the way this looks. We'll improve it at some point in the future, you know. Perfect. All right, so going back to the motion controller, because the goal here is that we won't need a sync byte, you know, moving in the future. Send packet, and we'll actually have to do some thinking here on. All right, so we can just delete this now. We'll make this a bit better in the future, but for now. Just back the robot back up. Remote control. Okay. Okay, we'll have to do a little bit of thinking here on how to do the reception because receiving on the motion controller side, just because we have this packet thread where we were looking for the type byte, but we'll have to receive the whole packet before actually deciding what to do with it. So what we shall do is reinterpret cast packet type. Yeah, all right. So what we do is well, nothing yet. All right, so rather than sending a sync packet, what we do is we're also going to not want to do this checksum remote thing. Oh, we don't want to raise an exception. We just want to return a none type essentially. But well, anyway. Okay. So actually, I think I'm going to, at least regarding, so the primary bulk data transfer is out of the Arduino. So we've significantly reduced, or well, I mean, we've increased the overhead probably, but we've improved at least a little bit the outgoing communication mechanism from the Arduino. So it's kind of funny. We've got this, old style kind of horrible transport mechanism towards the Arduino, and then actually, okay, hold on. Before I say that, we'll send if default. Yeah, because the problem here is if we get a packet type that we don't understand. Well, okay, so okay, so yeah, basically what I'm thinking about right now is that the way that the commands going to the Arduino is the same thing as the commands coming out of the Arduino. Or was the same thing as the commands coming out of the Arduino. It's this: we send the type byte, we send the data, we send a checksum. So the thing is that the old logic looked at the packet type, and then it looked at the packet type, tried to receive it. If it failed to receive it, just assumed that the packet that was intending to be sent was that first byte. And if it failed to receive correctly, it would then send an error with that send type. Now we don't necessarily, if the contents of the packet are garbled, realistically we just need to send a NAC in general that the last packet sent was garbage. And how did I handle timeouts? Because there's like a set throttle. This command, like if I wanted to say set throttle or get loop create future command future queue, put no wait, send packet, wait for the future command future queues. For type of packeting keys, add a queue. And so if we don't get a response, we assume a timeout, and then we resend. If we get a NAC packet, yeah, we could handle command errors as basically just timeouts. Like there will be no definitive response from the Arduino upon an error. We could definitely do it that way. I think we'll do it that way. All right. So yeah, let's implement COBS coming out of the Arduino as well. Or going into the Arduino. Sorry, come out of the Raspberry Pi. All right. So we've done our transmit packet. Now we need to implement receive packet. The receive's able to not worry about because we just need decoded data buffer. 4 block. Assert buffer, encoded byte, input buffer, byte. And the length we just don't know. Yeah, so let's just do it this way. So we're going to implement a receive packet function here. Template, type name, Jan, type name T. Bool receive packet, channel, need packet. Okay. And so what we'll do, we also need a packet type. Okay. Packet type, packet. Actually, we'll just prevent that. We'll just do it this way. Okay. So basically, packet is the buffer, and then type is the type of packet that we ended up receiving. So, actually, I take that back. We don't even know what type of packet we're trying to receive. We don't actually care what type of packet we're trying to receive. So actually just channel bool receive. What we're going to do is we're just going to take a score t pointer to data, and then a size t pointer to essentially the length of that buffer. Okay, so what we'll do now is, I wonder if ChibOS's channel read has a read until. So ChibOS and read. But I guess that is trunk. So asynchronous, read timeout, read. Okay, there's no read until, so cool. So what we'll do is by is buffer. Well, we don't need that. Decode. Okay, pointer to the decoded data. uint8 decode equals data for uint8. Code is ff. This is block. What was block defined? What? Alright. This block, fetch the next block length. Oh, right. You can do multi-declaration like that. Okay, sorry. I hate that. I've always hated that. And byte is less than buffer plus length, but we don't actually have to worry about that because actually even need to. Realistically, this is just uint8 code. I'll just do minus block at the end of this. We'll then do first thing we'll do is we'll receive a byte. I don't know if there's a chan read. Let's go back to this documentation, GBOS. There a read byte, is there a read single, basically? Is there a stream read until? No. No, it's always going to be. Oh, there's a chan get. Channel blocking byte read with timeout. Ah! Perfect. Chan. Ah, well, there's a channel get timeout. Okay, so cool. So we're gonna do auto byte equals chan get timeout channel time infinite and that's it. All right. Perfect. We'll undo. Receive a byte if block, then decode plus plus is byte. Else block equals byte. If block and code not equal FF, we got decode plus plus is 0. Block. Aye. That's the end of packet. Perfect. Yeah, end of line. I'll do just to note what's going on here. Cobb's decoder data. Okie doke. And then what we're going to do is we're going to do auto or basically, we're going to set this while condition to make sure that we don't overflow whatever buffer we gave it. So while the decode pointer is not equal to the, since we can only increment it by 1 at a given time, while the decode pointer is not equal to our data pointer plus the size we gave it. So size t length is decode minus data, and we're going to assume that the last byte we get is always a checksum. So if length less than 1, actually, honestly, if it's less than 2, it can't be a valid packet because, well, if the length is actually, yeah, if the length is less than 2, then we can't. It's empty. It's just a checksum, and it's just a checksum. And then so yeah, if it's less than 2, clearly it's bad. So then what we'll do is else. Or actually, I mean, if it's less than 2, so what we'll do is we then do uint8 crc8 equals calculate crc. Always start at 0. We actually have a data block, so data. It's always going to be length minus 1, just because of the checksum. And then if, yeah, and then return crc8 equals decode equals, yeah. Data length -1. And is crc8 equal to the last byte of our decoded packet? Or of our decoded packet data. All right. So yeah, we verified it with this. All right, hopefully that works. Receive packet. Receive packet will always receive a full block. So that means we're gonna have to rejigger a little bit of this. We still, I mean, that's gonna be a lot of breakages, but no errors inside of the function. Or it didn't look like there's any errors inside of the function. So what we're going to do is bump up the working size of this thread again, because we're going to use a packet buffer in here. So rather than doing all this, we're going to say uint8_t buffer 64. I'm pretty sure all of these can fit in orientation. Actually, I'll just say 128, man. 96. And we'll say if receive packet one buffer, size of buffer, and then we'll say packet type is buffer 0. Switch packet type, and then we're going to say handle configuration set. Pointer to pointer to. Oh, this is gonna be fun. Reinterpret cast. Actually, for now, we're just gonna chunk it a buffer. This one. And honestly, the sync packet will be gone. Actually, we'll just comment that out. Oh, this is buffer +1, just because we have to implement all of this processing. All right, so uint8_t buffer. No arg argument packet. Oh, lovely. Say command packet is equal to interpret cast pointer buffer. Oh, that's wrong. Oh, this is just feels disgusting. And the whole bad checksum thing, we're not going to worry about sending bad checksum necks anymore. We'll just be quiet. And then UNT buffer. Let's say command packet equals reinterpret cast. Okay. Okie doke. Hopefully almost there. Packet equals pointer interpret cast, command packet. Disarm. All of the people who program in memory safe languages are probably screaming at their monitors at me right now. This is definitely not memories. This is definitely a bit of a stretch. But again, hobby code, and also we will fix this later. We'll fix this. This is just hacky changes to no argument packet. Oh, it's literally just an empty packet type. Nice. Yeah. I do. All right, last one. Okay, there we go. Cool. Now, just to make things a little happier, we'll do a const. Alright, cool. Well, it built. I don't know if that's a good thing or not. Clean. Okay, so it did build. So now we need to change our transmission function on the in the Python code. Well, actually, sorry. So make. Well, actually, let's use all my cores. Make SCP. Bring that over. And then we shall. I really should have committed the COBS receiving logic before I hacked this up even more. So, oopsie. Again, if anybody watching, you have questions, comments, whatever, please please just type in the chat. I do try to keep an eye on it. Nice. So we built that. Now we need to do our send packet. I synchronize. Right now, writer. Right. Okay. So send packet. Perfect. So what we'll do is we do a byte array. We then this is easy. Then extend with we do data as a byte array. Do our send type. Do our size of extend our data. Do our hash. All right. So this is easy. This is easy. So COBS. Packet COBS. Or data COBS. COBS.encode data. Actually, that's another good question. If we were to say Python from COBS import COBS x equals or s equals binary string hello world. We do COBS encode s. We see our encoded string. We would say c equals that. If we were to say c dot extend, that's not the right type. We do b buff equals byte array. I don't think that works either. Extend. Perfect. Can I append Python? How do I Python append bytes? Can I just add them? Let's see. Oh. Okay. That's easier now, I thought. Right. COBS.encode data plus. Okay, that was easy. Perfect. That was easy. Okay. Okay. So let's say AVR dude flash that motion controller logic. I need to get rid of that synchronize function. delete synchronize. Delete the call to synchronize. What happens if we run remote control now? Oh, damn. Ooh. It's all bad now. Canceled, future.result, trace back, set config, get config. Wait for, I guess the timeouts. I could type ID. Actually, you know what? Let's p-type. Let's actually ensure that we have the checksum before we do that. Async def receive packet. Packet ID. And do try. If we get an invalid checksum error, just do a continue. All right, cool. Oh. That's always, it's a timeout anyway. Sleep. Oop, that's a problem. App.run, configuration. Still a timeout error. Okay. Stuff is happening. Stuff is not happening. But all right. So if we do a receive packet, we go there. We're going to just time.time. Okay, well, we are receiving stuff, but those aren't the results of commands. We're going to try sending a configuration get command packet. Which has no data to encode. It's just a type and a checksum. Okay. W. On wire. Cool. Yeah, partial received and valid checksum. Kill switch. So, failing to respond to Steph. Yeah. Handle packet sync. No sync packet, receive packet of a buffer. Sync buffer +1. Configuration set. On wire B. X11. All right. Configuration set. If local state is disabled. But we're not picking this up. We're just sitting here in a loop. If not, receive packet. I decoded this wrong. I mean, I could have easily decoded this wrong. It's not like we have a way of debugging this right now. Verify checksum. Current viewers one. Alrighty. So we've got this. Let's see if we can. No, yeah, let's transmit some kind of something. Okay. And command and packet. Timeout, timeout. Yeah, so what's interesting is that see packet status, packet status, packet. And you just gotta wait longer for it to wake up. Wait 2 seconds, just see what happens. Oh, that seems to be. Oh, that's working. We just had to wait longer for the thing to boot up. Alright, that's funny. That's funny. Alright. There's packet status packet. Huh. Interesting. Oh, this is only if I... actually decode successfully a packet I don't understand. Oh, jeez. Okay. No wonder it's not sending me anything. Packet type. Packet type. Honestly. This is a, checksum. We'll define this unsupported packet type thing just so we can cover that command that we just implemented. Failure type. Yeah, failure type. Unsupported packet type. FE. Support packet type, and then we'll just do a none packet just so we can detect what's going on. Hold on, where are you? Yeah. Type none. Let's see what happens here. Make. Alrighty. Yeah, I'm curious. Okay, received. Yeah, there we go. Mac packet. Command type 0. Yep. Failure ID 255. What happens if we change this back to oh, sorry. 1 second. So timeout. 1.5. Yeah, just 1.5 seconds. Maybe I'll check some. Partial receive. I don't like. Yeah, I don't like. Yeah. NAC packet. Yeah, there's going to be probably a failure. Yeah. Key error. Yeah, there's going to be a key error because it's an unknown type of packet that we're transmitting this as. So if you've got a NAC packet type, we probably should define a as a call this a framing error packet. Realistically, there's no and honestly, we're gonna have to. There's no fields. It's an empty type. This is a. Ugh. Okay. We'll define the type of NAC. I'll say type framing error. Call it an E1 packet. And then we'll come back here. We're going to do motion controller types. I'm going to say a framing error. E1 packet. Where's our NAC packet? Actually, to be honest, because this could be a checksum error, a framing error. Honestly, knack packet is kind of... honestly, we should just call this a bad checksum packet. No, it's not a thing to do with endian. It's just transmission. Just this packet type would indicate that either the checksum didn't, this packet would be transmitted if a bad checksum was detected. But because we don't know what type, because the data is bad, we don't know what type of packet you were trying to send. So we're just going to call it a framing error or a bad checksum error, or what do you call this? Actually, let's just call this a checksum error packet, because it's not really a framing error. No, framing error. It's a checksum error packet. Yeah, checksum error packet. Cool. Put this as a packet type checksum error. Some error packets. Cool. CP Nice. Unsupported. And we'll send that. We'll flash the code. And then we'll try to run remote control, see what happens. Cool. And it's generally running. Hopefully, at the beginning, we can see a checksum error packet. Perfect. That's what we want to see. Because we are the reason we want to see that, right, is that we were adding this extra packet end, which means we're sending empty packets, which should result in essentially bad packets, or erroneous packet detection, or triggering erroneous packet detection. So, so we send a packet, get configuration, get command. We put this packet delimiter, which forces the packet receiver to get an error. So yeah, we received a packet loss notification. We receive the configuration packet. We then send the we send a get configuration. We should receive an error and then a proper packet, and then we send a configure packet, and again we get a checksum error packet. Then we receive a configuration set ACK. Please arm to move forward. So yeah, so what we shall do is we can now remove this. We'll remove the on-wire bit from that just so we don't change that line of code. Okay, and then we'll leave this this something went wrong junk in here just so we can see that something's going on. So yeah, we should receive 2. Cool. And then we get packet loss notifications, and we're still actually the robot's still actually functional. So we are in fact handling errors, which is good. And now we'll remove the send junk thing, right? So where was that? That's up here. Yeah, we don't want to do that, right? All right, so just do that, copy that in here, and restart this logic. Yeah, and no bad packet stuff received, right? Or generally no bad packet stuff received. Cool. But we do still get that idling. And so what we're going to do is, rather than calling that one packet as a sync packet, we're now going to... Actually, we'll leave that name to sync, but now we can change the meaning of a sync packet now. And now it's just an empty packet. Actually, you know what? We can just leave it as full of junk. Maybe we really didn't want to delete that synchronize function, just from the fact that we need it. We should have a way of at least pinging the while. We don't want to directly read this thing though, so we want to send we want to have a command type packet called sync, at least ping. Actually, we will, rather than calling this synchronize, well, we'll leave that function there, but what we will do is we'll send, I'm not calling it a sync packet, we'll call it a ping packet. I don't want to rename things if I don't have to. But we will send on this side case packet type. We'll restore this sync, right? And that'd be handle packet sync, right? Yeah. we'll restore that. And yeah, and then we'll come up here to send sync packet, which is just not worry about that. Yeah, handle sync packet. Let's say packet. Hold on. Okay, handle sync packet, using response packets. Sync packets. All right, cool. Perfect. So that should be, we'll transmit a synchronization packet, and because it's going to be a send command, it will put a futures in the send type. Okay, perfect. And then we wait for, so rather than the synchronize function, what we do is we can literally, rather than doing this wait, we do await, send command, sync packet. Oh, self.send command sync packet. And that should handle the startup synchronization. So copy that over to the robot. Oops. Flash that to the motion controller. Oops. Actually, what we'll do, this is going to be, we got to fix that. We can't leave it like that, but because that's not good. It's not working because it's stuck forever. I'm curious. Yeah, wait for timeout, send command, controller start. Yeah, we don't even have a time. Yeah. Just to try to hack this up here for a second. Partial received. I'll turn on this debug message again. So we're going to turn on the send packet debug too. Oh dear. All right. So where did? Oh well, we received a sync packet. Oh, I see. Well, what? I mean, there should be a queue and sending a command. Oh, okay. Oh, wait, no, there is a send type, packet type sync. Oh. Oh. And we are transmitting. Yeah, we have no, we're not supposed to have any fields. Sync packet. Yeah, wait. Hey, what's going on? How come we timed out? We received a packet, a sync packet, received packet. And else is checksum packet, else is orientation packet, is status packet, command futures. Basically, this command futures structure should be receiving. There should basically be a list of I've sent a command. I'm waiting for a response. I don't know why it's broken on. Oh, it's because I did that. Ah, booger. Okay. That's why. It's because it was just bailing out early. There we go. Now it's happy. Now it's happy. Okay. Yep. Send command equal, yeah. 4 in range. In right? It's for I in range. For I in. Right. Yeah. In. Yeah, start, stop, 0, 5. Yeah. That's not working. Oops. Oh. Honestly, we'll come up with a better method of synchronizing here at some point. So the problem is that if we have a timeout, send command. Yeah, if we have a command that fails due to timeout, we want to remove the future. Are these duplicates? What the hell? Okay. Well, let's check some error. Send command. Let's go to send command. Let's see. Okay, async queue. Oh, I see. Yeah, because the problem is that, we put it into a queue, but we don't know if it's been canceled. Return await. Because the problem is if we raise if we do actually get the sync command and we raise the coroutine. Problem is the future's already... Yeah, the future's already gone. Loop. I think what we need to do is, if we have a timeout, we have to cancel the command. We got we try that. And then if get no wait. Else raise Q empty. There we go. There we go. That looked like it worked. Send packet sync, send packet sync, send packet sync. Receive loop. Oh, perfect. Okay. That looks like it worked. Nice. So we'll... Perfect. Okay, awesome. So now we have a proper synchronization routine. Essentially what this is doing is it attempts to send these commands. If the command returns a timeout error, it will just keep looping. If too many attempts pass, then it will raise a connection error. Actually, we can raise a timeout error. We'll raise a connection error. And then I'll just recomment that out. Recomment this out. And then send command will, upon, if it fails to, if it fails to get, if it fails to receive a response in time, timeout error will occur. It will then cancel the future and then re-raise the timeout error. Let's see, Python handle do something on exception. Try without catching. Is that a thing? Is that a thing? Sorry, what I'm trying to do here is I don't want to actually catch the exception. I just want to do something if the exception happened. And then re-raise the exception. So whatever. And re-raise. This is the Raspberry Pi Python code, not the Arduino. Unfortunately, King Crimson that joke is flying over my head. Yeah, so we create the future, cancel. Really, I just want to do something if an exception happened. I don't actually want to stop the exception because I want the caller to also have to deal with something. So anyway, so yeah, and now it will keep trying. I commented out the knack packet because I think that this logic is supposed to also handle this also handles knack packets, and so while this is while there's probably a better You know what? Let's see what happens if we ask Claude. I'm curious. Okay. Given this Python snippet. This Python snippet. I'm curious. Are any of these better? I don't think any of these looks I don't think any of this looks any better. Never mind. AI, useless. Okay. Alright, well, I mean, this works. It's just ugly. Realistically, I want to keep looping. I hate wild trues, but either way. Basically, the idea here is that we keep reading these command futures until we find one that's not canceled. But anyway, so this appears to be working. Then it'll back up. And then if we do find cone, maybe we uh-oh. That didn't work. Oh, now it's working. That's funny. And it is, in fact, driving the cone. That worked, but I'm also kind of... What is that? Clearly, something is not quite right. Connection error. Oh, debug. Not enough bytes for length code. Oh, so it received a 0. Okay. So packet cobs. Less than 1. And we can just then it's nice. Anyway, all right, remote control. Okie doke. Okay. Cool. Nice. Okay. We'll work on that a little bit more in the future. But anywho, all right. So let's just commit this work that we've done. Git add dot git commit dash m migrate to using cobs for serial packet framing. Okay. Oh, well, damn it. Okay. Let me do git. There's something not nice. Nope. So go in here. We'll delete that template block that we commented out. And then we can do git add dot. Actually, does it still build? Yes. Git commit dash m migrate to using cobs for serial packet framing. It's the same comment I did on here, right? Migrate to using cobs for serial packet framing. Migrate to using cobs for okay, and push. Then we'll just do a git push from here. Perfect. All right, now that code is committed if y'all want to check it out. Perfect. So now we can actually start to check out the USFSMAX. Finally. All right, it is 9:50. That's fine. All right. So now, let's see. So we have this in the Greg Tomasz GitHub repository. We have, actually, before we even get into this, I do have a little bit of pre-existing work regarding this USFSMAX, but none of this worked. I mean, it kind of did, but I don't know if it's any good. So I'm going to actually come in here and I'm actually just going to delete this. Boop. And then in motion controller types, I believe there is a type of packet. Yeah, we're going to have to remove that. And we're going to comment out this orientation packet because it did use some of that USFSMAX logic from before. But I believe this is fine now. Make clean. Yeah, all right, cool. And so we're going to start by creating a drivers directory. New folder. Drivers. And then new folder. USFSMAX. And the whole idea here is that most of the IMU logic the vast majority of the IMU logic actually is handled on board this module. There's a microcontroller inside along with the accelerometer, the barometer, magnetometer, and such. So, okay, let me just close this cobs stuff. All right. So they provide, or the guy who created this provides a sample project essentially that lets you use the sensor on a teensy or on a teensy Arduino basically. I don't know if that's its actual name. Teensy 4.1. It's called a teensy. It used to be called a teensy Arduino. I just don't know if they got in trouble for that. Yeah, it's just called the teensy now. It's a teensy 4. I mean, it's a fast board, but it's based on a teensy 3.1 or this sample sketch. So the idea here is that this is a host utility tool for configuring the sensor. And so the idea is that I want to split this into a utility application for that basically written in Python on the Raspberry Pi, and then the actual like sensor bridge that runs inside the motion controller. And all of this logic is basically implemented such that, you know, it's built to run entirely on the target device, which we don't really want to do because it's a serial console, and we have our packet interface that we've built, and so we want to go over that. So the idea is that we're going to try to lift as much code out of this as possible, and then we'll make changes where needed. So the first thing that we really ought to do is look at migrating the utility classes that are in here. So not this, I don't think this sensor calibration thing actually is needed in the base component. It's a lot of this coprocessor configuration thing. A lot of USFSMAX Unified Sensor Fusion Solution, I believe he called the Ultimate Sensor Fusion Solution. Yeah. And it takes an I2C device or dev, but that's a class that has been written for this board. So we'll have to adapt this to running on top of ChibiOS. So I think what I'll do is I'm going to come over to my computer here. We're going to go to the sources directory in my machine. Where did I put the USFSMAX code? I don't even know if I... Oh boy, sorry. I hate folders that I'm not using. It bugs me. I don't know why. Doesn't look like I got it. So git clone this. All right, so USFSMAX. All right, so we have the code. We'll open a file. Sources. The C module. CSLD for 3.3. And obviously none of this works because... Okay, well, what we'll do is... It'd be really cool to implement one of these sub things as like a teensy, or as a ChibiOS thing, but whatever. What we'll do is we will... see, copy MMC... star to cool. All right, so now we've put all of this under drivers, and so config all of this stuff, Oh, interesting. Okay, so USFSMAX. So yeah, we'll go in here. Let's config. Dev. Perfect. Okay, so we'll just make this use the teensy stuff. Okay. Okay. Interesting. I don't know why this is being funny. Anyway, we shall include HAL I2C. Well, who knows? I2C dev. Our own I2C dev. We're going to do I2C.h. And then we'll go there. What we'll do is we'll just start by including stuff in here. Motion controller, include driver / USFSMAX / I2C-dev.h. Let's see if that does anything. Yeah, okay, cool. I2C-T3 is bad because it's not defined. So what we'll do is I2C dev. Oh, no, wait. That's I2C driver. That's what it's called. Good. Cool. Make nice. All right. You can include that correctly. We're going to all of this serial.print stuff is going to have to be removed. I'll have to add this as stuff over time. We'll hack it together for now. All CPP ops. Cool. We're going to delete Arduino. We're going to do driver. Perfect. What if these have all the extern C stuff? Yeah. All right. Cool. Def. Nice. Okay. I'm trying to make the minimal changes as possible right now. Actually, yeah. Oh well. Oh well. Whatever. I2C driver. I2C stop. Okay. Cool. 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 And transmission request from byte. Okay, now we need to change this over to how Chibi works. So we'll do that. So over to I2C dev. Read bytes. Store register data. We'll do stuff. This is going to be the type of read current sensor. Just say it's submit I2C bus address. Where's actually time infinite come from? Oh, CH. Okay. Wait, hold on. If I do comment this out, where does it complains about mutex looted from how I squared C. Okay, yeah. Okie doke. I think OSAL needs halconf, right? No, it just needs CH. All right. Halconf, yeah, something I define. All right, cool. Ooh, this was bad. Thank you. However, okay. List the data, read bytes. List I++. Oh dear. Count. To be different. Sub address. Okay, write bytes, begin transmission, write bytes. I hate that. Okay, well, rather than I2C dev, how much I2C dev is needed? RG read byte. RG read bytes. Because that's not efficient. Oh. Yeah. Why? Okay. You know what? Screw this. We're gonna delete I2C dev. Move to trash. There's already an abstraction layer for ChibiOS. So what we're gonna do is come back here, comment out that thing. We're gonna go to makefile for all the things this needs. So I2C dev. Let's start with porting alarms. Yeah, let's start with porting alarms.cpp. Makefile. Honestly, alarms. What is alarms even used for? LED pin mode. LED pin mode on. TOF toggle. Alarms. Literally in the. We're also going to delete all this alarms stuff too. Ugh. Okay. IMU, USFSMAX. So it looks like USFSMAX is now the base type. All right, so makefile USFSMAX, and we will include USFSMAX. We're going to remove alarms. Do I2C driver. And we're definitely going to want assuming uint8 or anything of this got used around here. It did not, so. Oh, wait, yeah, it is. Anywho, we'll include those. And remove Arduino. This is ITC driver. Firmware ID. Okay, we're going to just disable the serial debug thing. Config. Oh yeah. Aye. stopped talking because I'm thinking. All right, sorry. I need to narrate more. Okay, so basically we're just going through here and changing all of the references to the old I2C dev device to ChibiOS's I2C abstraction. There's obviously some API differences, mainly in the single byte operations. So I'm trying to remember and see how to do these inline array declarations. I think it's like I can't even remember. Whatever. But we're gonna try I2C master transmit to C 32660 TX buffer. I think it's like fusion start stop. I remember. Oh, redeclarations aren't allowed. Okay. Can't remember how this worked. Ah, that's what it was. What C standard is this using? Compound literal. There we go. There we go. Compound literals. All right. Do I need to keep the makefile adjusted, or was it fine? Cool. Good. Cool. Cool. We can clean this up with compound literals. Nice. All right. Any returns in here? No. I2C release bus. All right. Config byte. Nice. That's what it was doing, right? Fusion, read fusion status. Read fusion status. Cool. Read byte. to sleep 01. Config buffer. Where's config buffer? What's that? Oh, geez, that's a big global. Okay. All right. Upload config. Oh. Okay. I see. Ooh. Okay. Upload config. Yeah, realistically, I see why. Okay, well, you know what we'll do. Use CoPro. Big data 0. Okay. Right. So the reason that it's doing this is I think there's a note in the datasheet that says it's just in order to make the uploads work correctly, or to make the upload more reliable, because some devices I2C engines have trouble with large contiguous operations. They're probably talking about probably some STM30. I have no idea what device, but the USFSMAX. There's a register datasheet here. They made the register blocks. Yeah. I'm gonna open this in. Yeah, there we go. And this coprocessor struct. Yeah, basically the first 30 bytes and the next 27 bytes, of course. It's 48. Or well, minus 30 plus 1 anyway. Huh. What? Right. Sure. Nice. So the config block's 48 bytes long, but it's 57 bytes in there. What the heck? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 29, 31, plus 12, 31, 41, 42, 43. Huh. Wait. 55 through 82. Something seems funky. Hold on. Something seems funky. Oh, of course. All right. Of course. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 21, 22, 23, 24, 25, 29, 30, 31. 31, 35, 39, 43. but yet it extends it to 48. Oh, funny. I'm surprised it didn't extend to 44, but whatever, I guess. Coprocessor config. Well, yeah, who knows? Maybe this is wrong. Maybe this is right. I don't know. Is there any more data sheet? Who knows? I don't know if I like that. Fun. Yeah, 48. Maybe they just did that just to reserve stuff for the future. Who knows? Who knows? So we'll just assume we did this right, which is kind of a terrible thing to do. But, you know, who knows? Who knows? So now, GXL. Whatever. Okay, so who's calling this? Nobody. Who's calling upload config? Sorry. Only itself, so we won't worry about locking the I2C bus. All right, so we're gonna do and then we're gonna master transmit. This is going to be MXL. GXL again. AXL. MXL. Okay, Q byte 0. Byte 0. Q0 byte 0. Lin XL. Borrow XL. Okie doke. Oh, oops. Right. There we go. 50. Almost there. Co-pro. Oh, yeah. 11. Yeah, it's definitely bad. Almost done with this file. We'll finish this file and then we'll call it for the evening. All right. And so, call this one. Do this one. Oh, hold on. Mess something up. Yeah, there we go. 0, transmit 30, do 0. That one. We're gonna copy this one, paste it here. Data 1, data 1. Full calibration. Buffer 30. All right. Mark out buff 30. Nice. Advanced calibration -3. All right, I think that might be it for that file. It is. Woohoo! All right. Perfect. Alrighty. So we have finished configuring this USFSMAX file. There's still a lot to do, or at least regarding some other, configuring some of the other stuff, rewriting the serial terminal stuff. But other than that, so made some good progress on this today. Next week we'll be checking out, finishing this up, and hopefully bringing that IMU online. So, all right. Perfect. All right. So this will be where we're ending. So good night, everyone. Thanks for watching. Please join again next week to finish this. All right. Good night.